Hello students, in this video we'll begin our discussion of orthogonal curvilinear coordinates. So suppose we have three functions. We have w1, which is f of x, y, and z, w2, which is g of x, y, and z, and w3, which is h of x, y, and z. We have these three functions of x, y, and z, right? And so we're going to say that the surfaces, so consider the surfaces, w1 equals c1, w2 equals c2, and w3 equals c3. These are all surfaces because they're the level sets of a function of three variables, so these are surfaces. We say that these surfaces are orthogonal and non-degenerate. I want non-degenerate as well if the gradient of w1 dot the gradient of w2 is equal to 0, the gradient of w1 dot the gradient of w3 is 0, and the gradient of w2 with the gradient of w3 is 0. And furthermore, I want them to be non-degenerate, so I want the gradient of w1 dot the gradient of w2 cross the gradient of w3 to be non-zero or strictly positive, so it's positively oriented. So they're going to be orthogonal if these conditions are true. And if I'm going to work in the system where these conditions are true, what I can do is I can look at the coordinate curves, right? I can look at the w1 curve that corresponds to the intersection of w2 equals c2 and w3 equals c3. I can look at the w2 curve in an analogous way, w2 curve that corresponds to what? Corresponds to w1 equals c1 and w2 and w3 equals c3. And then finally the w3 curve is going to be what? The w3 curve is going to correspond to the case when w1 is equal to c1 and w2 is equal to c2. And these curves over here are going to be orthogonal curves to each other. So these curves are orthogonal to each other. So these curves intersect orthogonally, they're perpendicular to each other. And so let me show you an example of a situation like this. I can look at a particular example. It's an example of this where you have orthogonal, these are orthogonal surfaces. If I look at x equals r cosine theta sine phi cosine theta. If I look at y equals what? If I look at y equals r sine phi sine theta, and if I look at z is equal to r cosine phi, these are spherical coordinates. Right? And we can find the corresponding formulas for r, theta, and phi, right? So over here we know what? We know that what this implies that r is the square root of x squared plus y squared plus z squared. From these equations over here, we know that the tangent of theta is going to be y over x. And then we know that the cosine of phi is going to be just a z over r, so z over the square root of x squared plus y squared plus z squared, right? And so we can show these level surfaces over here, so we can show that r equals c1 are spheres. These are spheres. Theta equals c2 are going to be planes. And what will phi equal constant be? So when you have phi is equal to a constant, if you think of the phi as a constant, those are going to correspond to the what? Phi is a constant, are going to correspond to planes as well. They're going to be conical shapes, right? So phi equals c3 are going to be what? So let's carefully analyze that because it's sort of easy to see over here. When phi is equal to a constant, for example, so in spherical coordinates, when phi is a constant, that corresponds to what? That corresponds to angles that look like this. Those values are constant, right? Those are my constant phi, and that means I can go all around like this, like that, and those are all the constant values of phi, right? So then we're on cones, right? So I have cones. And we can check that these surfaces are all orthogonal to each other, so these are orthogonal. Okay. In future videos, we'll figure out how to compute the Lemay coefficients of these orthogonal curves, and that will help us compute differential operators with respect to these coordinate systems. Thank you very much.